Back to Mathematics 0110. In this lesson, we're going to talk about how to take the derivative of these weird looking functions here. There are different types of exponential functions, and the rules and strategies that we've learned so far for taking derivatives, they don't apply to these functions, and I'll show you why. So back in the day, whatever that day was, we looked at this definition of the derivative as a starting point. The derivative is defined as a sensitivity of the rate of change of the y value to a small change in the x value. The top of this expression, f of x plus h minus f of x, that's the difference between the value of the function at some coordinate x and at some coordinate x plus h. So we add a little tiny bit to the x coordinate, and that's f of x plus h. And f of x is the value of the function at the original x coordinate. Then we divide by h, and h is the difference between the two x coordinates that we're testing. This is a delta y over delta x, which gives us a slope. And this is how we've been defining the derivative all the way through. Now, I want to show you how this definition necessitates a different formula for the derivative. I'm going to shrink these down a little bit. Okay, so I'll show you how that works for x squared. I think we did this one. I'll start by saying that f prime of x is the definition of the derivative, limit as h approaches 0, f of x plus h minus f of x all over h. And now you know what the answer is. You know there's a shortcut. You know the derivative of x squared is 2x, but this is how we used to do it. So, for old time's sake, we'll do it this way again. Limit h approaches 0. F of x is x squared, so f of x plus h is x plus h all squared. And f of x minus x squared over h. Now we have to expand the x plus h squared. We're going to do a FOIL. We get x squared plus 2xh plus h squared. And then minus the x squared that was already being subtracted, all over h. We get two pieces disappearing. The x squared and the negative x squared destroy each other. So limit h approaches 0. We can't let h be 0 yet, because if you look what happens, 2xh plus h squared all over h. We have 0 on top and 0 on the bottom. So 0 over 0 is an indeterminate form. We have to do something. Unfortunately, the thing that we have to do here is just common factor. On common factor an h from the top, and I have 2x plus h all over h. And now we can cancel the h top and bottom. And finally, we have the difference quotient, 2x plus h, which we can now let h equal 0. Now the limit operation can disappear once we replace h with 0, so 2x plus 0, and we get the answer that we could have got with our shortcut in one line, 2x. Now what happens if we interchange the position of the variable and the constant? So in x squared, the variable is in the base, and the power is a constant, in this case 2. What if I switch those? So the base is 2, and the variable is in the exponent. So what if I change it from the polynomial on the left-hand side to the exponential function on the right-hand side? Let's go for the same definition of the derivative and see if we get something different or if we get the same. Limit as h approaches 0 of, I'm going to write down the definition again because it's good. It's a good habit. When you're solving problems in mathematics, it is a good habit to write down the definition that you are going to use. For example, continuity. Show that the function is continuous at 3, or find the value of some constant that would cause the function to be continuous at -8. Starting with a statement of the definition, if that's all you had, that's a mark, because that tells the person grading your stuff that you know what you're supposed to do. You are supposed to satisfy that definition. Anyway, here is the definition of the derivative. Now I'm going to plug in the particular components for this function. Our function is 2 to the power of x. F of x plus h is going to be 2 to the power of x plus h. So limit as h approaches 0, 2 to the power of x plus h minus f of x is 2 to the x all over h. Right, and at this point, we look at what we had on the left-hand side. We foiled on the left, and we can't foil on the right. There's something else we have to do. Another thing you might try as well, let's just take the limit. Let's replace h with 0. So on top, we have 2 to the x minus 2 to the x, 0, divided by h. Well, we just replaced h with 0, so that's also 0. We have 0 over 0. It's indeterminate form. So there's something we have to do. Now, the thing that we have to do here is we have to use a law of exponents. We have 2 to the m plus n. We can rewrite that as 2 to the m times 2 to the n, or in this case 2 to the x times 2 to the h, minus 2 to the x all over h. And now we can common factor. I'm going to common factor 2 to the x out, and we're left with 2 to the h minus 1 all over h. Okay. Now, if you look back at the notes, or if you flip to the textbook for limit properties, this is going way back to when we started talking about limits in section 1.5. One of the properties of limits that we've used frequently when working with limits, but we tend not to talk about, is the property of factoring stuff out of limits. Now, I said back then that we can factor a constant out of a limit, but it's a little bit better than that. We can even sometimes factor functions out of limits. This limit is telling us to let h go to 0. As far as that limit is concerned, I know 2 to the x is not a constant, but as far as the limit is concerned, it is. Like, the limit is telling you to do something to h, not to do something to x. So if we take the 2 to the x out front of the limit, we're not going to change anything. We're not going to violate any mathematics. 2 to the x comes out because it does not contain any h. And then we have the limit as h approaches 0 of 2 to the h minus 1 all over h. What is this? What is that limit? We could attack the idea, just plug in 0 now. So 2 to the 0, 2 to the 0 is 1. So 1 minus 1, 0 on top, divided by, we still have 0 over 0. We haven't gotten rid of the problem. And sadly, we can't get rid of the problem. What we have to do is we have to define the problem away. I'm going to give this quantity a name. I'm going to call it ln 2. And it actually is the ln of 2. Comment. Ln 2 equals the limit as h approaches 0 of 2 to the h minus 1 over h. Ln 3, take a guess what ln 3 is equal to in terms of a limit. Limit as h approaches 0 of 3 to the h minus 1 all over h. I want to show you in Desmos. Desmos is for graphing, but you know it's also a calculator, and I like it for calculations. So let's go with convincing you that this thing is equal to the ln of 2. So I'm going to say ln 2 here, and it's going to spit out what the decimal representation is, 0.6931, blah, blah, blah. Now I can't take the limit to 0 using a calculator. What I can do is I can let h be really, really small. So let's say h is equal to 0.001. So 3 zeros after the decimal place. Okay, and then I'm going to say 2 to the power of h minus 1, put that all in brackets, all divided by h. Now it's not perfect. It's not perfect. I have 6931712, and up above I have 69317 instead of 171. So they're off a little bit, and it's off only because h is only 0.0001. It's not small enough. If I make h smaller, So I'm going to add more zeros and watch what happens. The quantity 2 to the h minus 1 all divided by h is getting closer and closer and closer to ln 2. Now I can change this. This is just for ln 2. I'm going to change this to a 3. I'm going to change this to a 3, and it's the same. So hopefully that convinces you that this quantity is ln 2 and that the other quantity would be ln 3. Okay, so before moving on, let's look at the difference here. We took the derivative of x squared and got 2x. We took the derivative of 2 to the power of x and got the same function back, 2 to the x, multiplied by a constant, 2 to the x multiplied by ln 2. And I should highlight that ln 2 is a constant. And the value of the constant was the value that was appearing before, 0.69, whatever. So again, we get the original function back times a constant. Very different behavior than a polynomial derivative. We'll come back to those types of exponential functions, to their derivatives. So exponential functions have bases like 3 and 2. But I want to spend some time right now talking about derivatives of exponential functions that have a base of e. So you go through the same work. If f of x is e to the x, then f prime of x is the limit h approaches 0, f of x plus h minus f of x all over h. Go through all the same work, like follow the steps that we just did with e instead of 2, and what you get is at the end e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Okay, and what is that quantity? So I'm going to put in this calculator, I'm going to put e there, I'm going to put e there, and they're both telling me that this quantity is equal to 1. Well, the h one isn't telling me it's 1, it's telling me it's 0.99999, but again, that's because this thing, see, it's struggling. It's, oh, look at that. So, I mean, there's a little mini lesson there about calculators. So look here. See, it's getting closer and closer to 1 if we make h sufficiently small. So let's go here. See, there's a value that's close to 1 on the bottom. Another 0, another making h smaller and smaller and smaller. The quantity is getting closer and closer to 1. That goes a little below. It's concerning. That's okay, I think. Actually, it's not okay, but it's not as bad as what happens next. And it goes up above and it's somewhat confusing. What is it doing? Add some more zeros, add some more zeros, and then it got bigger. And then it got like weird. What's going on? And more zeros, and now it's 1.11. I'm making h smaller. What's going on? What's happening is the calculator is failing. Now it's completely 0. Calculators have problems with all types of calculations. We hide that from you. We tell you that calculators are okay, but they're really not. They are flawed devices. Your brain far exceeds the computing power of the most powerful calculator that exists. And that's probably going to be the case for humanity for a long time. Our brains are remarkable. Even if you don't think you're good at math, you are better at math than the most powerful computer is. Anyway. So this quantity, limit as h approaches 0 of e to the h minus 1 all over h, that's ln e. E to the x times the ln of e. But what is ln? Recall that ln of something means log base e. It's a shorthand. So we have e to the x times log base e of e to the 1. Put a little power there. There's no power on e, so we can put a power 1 on it. And now we can use the cancellation law. Log base e of e to the 1. It just gives us 1. And we get our final answer which is probably why the universe likes e, the number e. The derivative of e to the x is e to the x. It is its own derivative. So with the previous example, we had the derivative of 2 to the x was 2 to the x times the ln of 2, and ln of 2 survives. Ln of 2 is not 1. Ln of 2 is 0.69 ... Here, the ln e is just 1, so it vanishes. It doesn't, I mean, it's there, but you don't have to write it there. You don't have to write ln e. We're going to take it and run with it. We're going to see where this takes us. If the derivative of e to the x is e to the x, we'll look at more complicated derivatives. So starting with this one, what is the derivative of 5x to the 5 multiplied by e to the x? The fact that we are now working with a different function type does not mean we have to go back and rederive or check our product rule, our quotient rule, or even our chain rule. Those rules were devised in ways and were derived in ways that are independent of the function type. It doesn't matter if they're polynomial functions or rational functions or radical functions or exponentials. And later on we'll see log. It works for log functions as well. So the product rule we had before is going to be the same product rule we have now. I'm going to call the first function in this product a, and the second function I'll call b. So a is 5x to the power 5. B is e to the x. We're going to need a prime and b prime. A prime is 25x to the power 4 using the power rule. And b prime, derivative of e to the x, using the rule just derived on the previous page, derivative of e to the x is e to the x. So when we take the derivative, we'll have a times b prime plus b times a prime. So a, 5x to the 5, times b prime, which is e to the x, plus b, which is e to the x, times a prime, which is 25x to the power 4. Sorry, just type. It's power 4. I'm going to simplify this by writing the constant up front, then the x to the power after, and then the exponential function last. That's standard form for mixed expressions like this. So 5x to the power 5 times e to the x, we get our original function back, plus 25x to the power 4 times e to the x. This is a great answer. I'm going to circle it because this is the type of answer I want you to have. But I'm going to keep going, not because I want you to keep going, but because many of you are checking your answers in the back of the book. And if you check your answer at this stage for a question like this in the back of the book, you're going to be like, what gives? What did you do? What they do, it's not a bad thing. They common factor. And there's good reasons to common factor. You'll see that soon. So that you can take a 5 out, you can take an x to the power 4 out, and you can take an e to the x out. And what are you left with? So there's 1 power of x left in the first piece, and there's a 5 left in the second piece, and everything else has been taken care of. So what we might do after taking the derivative is we may do something like set the derivative equal to 0 and solve for x. And having it in factored form would make it easier to do that. Okay, let's keep going. Another one. Here's g of t. So t is going to play the role of our variable instead of x, and that's okay. Now our function is a square root function, and that's also okay. We know how to handle those. We'll replace the square root with the power 1/2 and then go from there. So this is e to the t plus 5 power 1/2. Now what does our chain rule say for these types of derivatives? Because we have to use a chain rule. This is a function raised to a power. So the chain rule, once we differentiate, will be the following. G prime of t equals, the 1/2 will come down. We will have our original function to one lower power. And then we have to multiply by the derivative of the inside. The derivative of e to the t is just e to the t. and then the derivative of 5 is 0 since 5 is a constant. I should annotate that. So d by dt, derivative with respect to t, of e to the t equals e to the t. Just like derivative of e to the x with respect to x is e to the x. That's a good answer. Perfectly fine. That can be left. I'm going to keep going. This is e to the t over 2 times e to the t plus 5 to the negative 1/2. I could bring that e to the t out front. I can just change order of multiplication. That's perfectly fine. You're allowed to do that. Next thing I'm going to do is that power negative 1/2. Well, power 1/2 is a square root. Negative means bring to the denominator. So I'm going to combine both things in one step. I'm going to bring that down as a square root of e to the t plus 5. So this e to the t stays up here. The 2 stays down there, and it is joined by square root of e to the t plus 5. Okay, we'll keep going. So far, we've had one type of chain rule. So our old chain rule was the following. I'll start with an example, and then I'll put the general format of it underneath. Say f of x is x squared plus 7x to the power of 5. Our old chain rule said when we take the derivative of such a function, the power comes down. We have the original function to one lower power, and then we have to multiply by the derivative of the inside. So the derivative of the inside is 2x plus 7. Now, if we want to write this in a more general form, say f of x is some function w to the power of 5. So w is a function. The chain rule written in this format is f prime of x equals 5w to the 4 times w prime. So look at the pieces. We have a w prime piece, which is this. We have the power 4, the power 4. We have the 5 in front and the 5 in front. So that's the structural format of the chain rule. Notice that it looks like the derivative of x to the power of 5. The 5 comes down times x to the power of 4, except it has the prime piece. We don't need a prime piece when we take the derivative of x to the power of 5, because the prime piece would be x prime, which is the derivative of x, and the derivative of 1 times x is just 1. So we'd have multiplication by 1. It's not necessary to show that component when we take the derivative of a power function, like x to the 5 or x to the 4 or anything else like that. But for a function to a power, we do need that piece to get the correct form of the derivative. So now I'm going to call it a new, and put it in quotes because it's not new, a new type of chain rule. It looks a lot like implicit differentiation, just like the above one looks like implicit differentiation. Think what you would do if that was a y to the power of 5. 5y to the 4 times y prime. These are all the same thing. They look different, but they're the same. If f of x is, let's say, e to the w. Well, the derivative of e to the x is e to the x. So when we take the derivative of this, we're going to get e to the w multiplied by w prime. It's just implicit differentiation with a different label. So an example, what would an example look like? Let's say f of x is e to the x squared plus 7x. Well, the derivative of that we have a derivative of e to the power of w, where w is x squared plus 7x. So what we're going to get out is e to the w, so e to the x squared plus 7x multiplied by w prime, 2x plus 7. I'm going to do the same color coding as above. So, should really match the colors though. Get some yellow highlighter for this part. So that's the w prime part. Oh, go away. Then I have orange. Oh, I guess I don't have an orange anymore. That's okay. And I don't have a green either. Oh well. That's all I can color code, so it matches up. Okay, so it's maybe not the nicest of notations, but it's the notation we have. Most other sources use the letter U instead of the letter W. And this is a form of long-term investing, to use the letter W instead of the letter U. If you do more math, this will pay off. Trust me. Okay, so I'm gonna be not using the above notation with the g of x, because sometimes the function on the left-hand side is called g of x. I'm also not going to use the notation with f of x up there because sometimes the function is called f of x. It's better to use a different letter like a u or a v or a w. I'm going to use the letter w. So the formula that I'm going to follow for exponential derivatives, where the exponent is a function of x, is this one. I'm going to say the derivative of e to the w is e to the w times w prime. So let's apply that to these examples. So the first one, we have w equals 7x. When we take the derivative of e to the w, we're going to have e to the w times w prime, which will be e to the 7x multiplied by 7, the derivative of 7x. And it's traditional to put the constant out front, so I'll do that, 7e to the 7x. Be mindful of what this notation means. The e is being raised to the power of 7x, but the 7 in front is not being exponentiated. So it's a constant multiplied by an exponential function, not 7 times e both raised to that power. Next example, right-hand side on top, w is x squared here. So w prime is 2x. We'll need that. When we take the derivative, we'll have e to the w times w prime. So e to the x squared times 2x. And then, as is tradition, I'll put the constant in front, the x to the power after that, and the e to the x to the 2 at the end. Okay, next one, bottom left. Here, w is negative 7x, so w prime will be negative 7. We take the derivative of the function f, we'll have e to the w times w prime, so e to the negative 7x multiplied by negative 7, and I'll put the constant out front, negative 7e to the negative 7x. Now the last one, our w function up in the power contains two pieces, x cubed plus x squared, but nothing about the rule changes. W prime is 3x squared plus 2x. Our derivative law is the same. Derivative of e to the w is e to the w times w prime, which is going to be e to the x cubed plus x squared times 3x squared plus 2x. And then I'll write it in standard form. I'll put the polynomial in front of the exponential. 3x squared plus 2x times e to the x cubed plus x squared. And those would all be the most simplified forms. There's no combining that you can do. And that's a good spot to take a pause, and we'll continue in the next video.